Hey guys, welcome to Unit 4, Periodic Table and Nomenclature, which means naming, by the way. And we are going to finish our unit with the periodic trends. We're going to cover 3.5 of the major trends that occur across the periodic table. First trend here is a parent trend, meaning it's one of the trends that basically determines all of the other trends, and it is nuclear charge. We want to remind ourselves the nucleus is made up of protons and neutrons, and therefore it has a positive charge. The electrons are attracted then to the nucleus. So we have our nucleus with its positive charge. The electrons, of course, are in their energy levels, and the reasons that they stay attached to the atom is that they do have an attraction to the nucleus. So the basic trend that exists with nuclear charge is the more protons, the more positive the nucleus is going to be, so the greater the charge of the nucleus is actually going to be. The second parent trend is shielding. We want to remind ourselves electrons are found in energy levels. As you move down the periodic table, elements have more electrons, and therefore, because of the arrangement of electrons and the number of orbitals, we can only fit a certain number of electrons at each energy level, and so larger atoms that have more protons therefore have more energy levels. Energy levels have negatively charged electrons in them, and so they themselves are negatively charged. And what that ultimately does is it disrupts the attraction of the nucleus. So if I think about my outer electrons, my valence electrons, they are attracted to the nucleus. But since there are electrons in energy levels beneath them, if they're at a higher energy level, they are going to have a slight amount of repulsion with those particular electrons. And so the attraction of, let's say, this electron to the nucleus is going to be stronger than the attraction of this electron on the valence level. And the only reason is because the first electron that I talked about is actually going to have a negative repulsion on the outermost energy level, on the outermost electrons, and it's going to kind of keep them from being as attracted to the nucleus as they could be. So energy levels reduce nuclear charge, basically. And so the trend basically is as you move across a row on the periodic table, shielding stays constant. Why is that the case? Okay, the reason that it's the case is because as you move across the periodic table, you add sublevels. So if I move, let's say, across energy level 3 on the periodic table, I start with an S sublevel. Then I start filling the P sublevel for that. Well, I mean, technically, I would ultimately fill the S, the P, the D, and the F sublevel potentially. So as you move across a row on a periodic table, you're not adding any more energy levels. You're just adding sublevels and orbitals to that same energy level. So they're not going to have that repulsion like you would if you were adding energy levels. As you move down a group, though, you are adding energy levels, and so therefore, I'm just going to put EL for energy levels, you increase the amount of repulsion from those inner energy levels. Now, how do we deal with this? Now, how do we deal with this interaction between nuclear charge and shielding? Every time we add an energy level, we're going to ultimately decrease the overall nuclear charge because every energy level is going to have electrons in it that repel the outermost electrons. And so when we're calculating this nuclear charge, that is the actual nuclear charge, we calculate it as what is referred to as the effective nuclear charge. Effective nuclear charge, we basically are going to take the number of protons minus total electrons minus the valence electrons, okay? So what you would do is essentially, let's say we're talking about sodium. Sodium has 11 protons, so it would be 11 minus, it should have 11 electrons, but then it has 1 valence electron. So what we see there is that since we have so many electrons in the inner energy levels, they are going to ultimately lead to the fact that we only have an overall effective nuclear charge of +1 for sodium, okay? Now, all of this has an effect on the overall size of the atom. Radius of an atom is a value that is referring to the size of the atom. And it's basically saying since atoms are roughly spheres, we could take the radius of it, and that tells us the general size of the atom. The stronger the effective nuclear charge, the smaller the atom is going to be. So as we see the trend, atomic radius decreases as I move to the right across the periodic table, because the nuclei on the right of the periodic table have more protons with the same amount of shielding as those on the left. So if I'm referring to, let's say, oxygen, fluorine, and neon versus lithium and beryllium, they have the same amount of shielding, but over here they have more protons in the nucleus. And so therefore, they're going to have a slightly higher effective nuclear charge and therefore a stronger pull on their outermost electrons to pull them in. As I go down a group on the periodic table, I end up with more shielding. And so as I move down, each successive energy layer or energy level is reducing more and more the effective nuclear charge, and so we see that the nucleus, Z, is no longer able to hold on to the outermost energy levels, and so they essentially kind of expand out a little bit, and that atom is going to be larger. The last idea that we'll look at is how the radius of an atom changes if we ionize it. So with cations, let's think about a cation. We're going to assume it has eight valence electrons, and let's say it has 1 valence electrons on the outermost level. Okay, so what we see is that if it loses that valence electron, then the overall size of the ion is going to be smaller. So if I have a cation, the atom is going to be smaller than its original atom was, or excuse me, the ion is smaller than its original atom was because it loses a whole energy level. In, let's say, a anion, 1, 2, 3, okay, it has, let's say it has 2, 3, 4, 5, 6 valence electrons, okay? And we're going to add 2 valence electrons to it. Well, when I add those 2 valence electrons to it, what they're going to do is cause more repulsion of the other electrons around them. And so that causes this to have to spread out a little bit and create a slightly larger outer energy level because the electrons are repelling each other. So when I create an anion, I'm actually going to have an ion that's larger than its original atom. Okay. I want you guys to write a short reflection about this, write what you learned about it, and write down any questions that are currently burning in your head. You'll put them on a Post-it note in the next class, and we will see you then.